27. I have here a force versus distance diagram, right?
Yeah.
So what should I immediately be suspicious of?
It's, yeah. Radius.
Well, we're talking about work, aren't we?
Yeah, yeah.
And I've told you before that if you're inside the planet Earth, your gravity is linear until you get to the surface, and then it falls off because you no longer have Earth above your head.
Yeah.
All right. The graph above shows the force of gravity is mass of a small mass as a function of distance r from the center of the radius or Earth. The Earth is assumed to have uniform density. The work done by the gravity, that work done. There's a force distance graph. So what should you be thinking?
Energy.
Energy, which is work, right?
Yeah.
No, work done. So the work done by the force of gravity when a small mass approaches the Earth from far away is placed into a circular orbit R2 is best described by the area under the curve between, so we're going from a very far away, from far away to R2 orbit. So best represented by the area of the curve between where and where?
Would that be, yeah, E to or E to R2?
Nope. This is a problem. It says the work done by the force of gravity when a small mass approaches the Earth from far away and is placed in a circular orbit R2 is best described in the area from where to where?
Oh. R2 to.
I think you may have said it. I'm not sure.
Yeah. R2 to infinity.
Yeah, right. So you're looking at E, hopefully. Check the key. Would never know. Drag force. Red FRQ2. Right?
Yes.
So you're going to be doing F net equals the sum of all forces. Right? You're going to remember in the back of your head that it's going to be an MA plus the force turning it, right? Is the portion of the force that's used turning it is equal to mg. Right? And then you'll look at this and go, well, okay, so it says linear algebra, so I'm sorry, acceleration, so I have to change this into it. We then go over here on the side, if we don't remember to memorize the formula, we remember that torque equals I alpha, right?
Yeah.
And therefore FR equals I alpha. So the force is equal to the I alpha over R. This is this idea that you have to, and when you're returning something with a normal force problem, that's what you have to deal with.
Plug that in.
And so then you're going to solve it, but first you got to change this alpha because it's rolling without slipping, or spinning without slipping. So we're going to change that alpha into an A, right?
So that's going to be.
So you go alpha R equals A. So alpha has to equal A over R.
So would the R's cancel out?
I don't think so. I think you'd have an extra R on the bottom. Now the R's will usually cancel out because usually they're going to give us information about the inertia, which will allow you to cancel it out. Because it'd be mR squared. But in this case, it won't. Because we're solving for A, how are we going to get the A out of there? Vectors. Using the right word and everything now.
So I'm assuming.
You wouldn't have to fix it on this particular round.
So I was gonna say.
Honestly, knowing this is going to be a lab question, I would circle this, but I would know eventually I'm going to have to suck this into a more normal equation. I don't have to look at it. They're going to say something like, you're going to have to graph the two axes, right? So you can solve for something, right? And so you're going to want to simplify this probably, but I wouldn't simplify it there. I'd let him have this lovely formula with a smiley face.
And then I'm kind of confused what B means.
What means?
B. It's like.
B. It says a time t is measured for distance, height, the square. It's flat distance d, right?
Yeah, that's like how it's flowing. But then it says what quantities should be graphed to the best determine the acceleration.
Okay, so we have an acceleration equation over here, right?
Yeah.
So I need to fix this equation up, right? So I can look at it a little better.
Yeah.
So I'm going to move that over. So I'm going to steal that idea. Change my color of ink so you have some chance of following what I'm doing. And then, do a common denominator on the bottom. Right? Then flip and multiply, and I'm going to get A equals mg r squared over m r squared plus I. Actually, you know what? I'm thinking we're not even need this because none of this has to do with I or D or T, does it?
That's why I was confused.
Okay, is D going to be, is acceleration going to be constant?
Yeah.
All right. What quantity should be graphed in order to best? So if I want to do constant acceleration, what's the formula I'm going to use?
D
D equals 1/2 AT squared plus V naught T. There's no additional velocity, so I drop that off there. I want to find acceleration. It's going to be 2D over T squared equals A. Agree?
Yeah.
Now, they gave you D and T. What's wrong with just graphing D and T? Yeah. It's going to be a weird-looking hyperbola. And I'm going to want to get data from it, right? So if I instead graph D over, or 2D over T squared, the slope of it would be these divided, right? Which would be what? Acceleration, right?
Oh, yeah.
So you're going to want to graph 2D with T squared, or you're going to want to graph D over T squared. Just realize you got to slap a T2 on there later.
Okay, I kind of misunderstood the question.
So the reason why I understand this question, and again, it's not a great question. The reason why I understand this question is because I know where they're going. What are they going to ask us to do now? They're going to graph them. They're going to ask us to take the slope, use the slope to find acceleration, and then maybe to find whatever it is we found earlier.
So 2D.
Here comes the graph.
At the point of like 0.5, it would be 1 for the y-axis. So is there 2?
Well, I'm going to grab. So first thing I'd do is I'd make another time, make a time. I'd square my times, right? Or 2D. Yeah. Okay. Fine. Yeah. Perfect. So I'm going to write down here 2D so they know that's what I did. I'm going to write over here. I'm going to write T squared, so I know what they did. And then I'm going to go 1, 2, 3, 4 on the bottom. And then I'm going to check T squared. T squared 1.38. I'm going to get my calculator. What's 1.38 squared? 1.9. So what's going to be the top of my graph on the left side? 2.0, baby.
Wait, why would you do 2D on the bottom?
Oh, I did it backwards. You're right. I'm absolutely wrong. Hold on.
Because you usually want to have time on the bottom.
Right. You want to have, well, not that. Look at your equation. We're going to try to find the slope, right? Rise over run. We want 2D to be the rise, right? Otherwise, we're going to flip the thing. They will let you do that, by the way, but then you have to remember to flip it, and nobody ever does. So I'm back to, this has to be 2 over here, right? This is 1, that's 0.5, and that's 1.5, right? And then on the left side, I'm going to have 1, 2, 3, 4. Okay? Now remember, you could graph it other ways. You could ignore the 2 essentially. If you do that, make sure you fill up half the graph. At least, both dimensions, at least half the graph. Otherwise, you lose credit for it. Yes, sir?
For like answering on part E for question 1.
Okay.
Is it fine if I left it as like their answer before the final line? Like I did 2m1l over m1 plus m2 plus.
The horizontal displacement x of a person, did you solve for it somehow?
Yeah, it's just like they're on the right on the second to last line at that.
Oh. I don't know. Does it have, let's say the variables you're allowed is m1, m2, l, and g?
Yeah.
So does it just have those in there?
Yeah.
And you have displacement equals?
Yeah.
Then that should be the right answer.
Okay.
I don't know why they go 2 more. Did they give points for after that point? If you look at the key on the right hand side.
So right.
For indicating that the horizontal displacement
plus
AD
one,
is
one's fine.
plus here.
Right. Okay. So you don't have to
No.
simplify it out of that.
No. Okay. So then you're going to graph a line, right? So get a ruler and go boop, 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 boop. Right? So they're just asking you to reassemble that one equation back to the inertia, right? So you just switch the direction of these two, take this equation, just flip there, those two are. Then move the mr squared to the other side. I think in the answer key, they actually bother to do this to clean it up some. And it's probably going to be a good idea. But it's not specifically speaking necessary. On the acceleration found in B3, okay, B3 was, we found the acceleration was, oh my God. They really want to put it in there? Maybe. That's not great. Sorry, what?
Well, in D, it's saying if you take the rotational, if you take a pulley and take away from its support, the rotational inertia is greater. And this is given explanation.
Okay, first of all, let's make sure we got C right. Are you good with C?
Yeah.
Okay, so you got C figured out?
Yeah.
Huh, all right. And the pulley is removed from its support, and its rotational inertia is found to be greater than the value. Give one explanation for this discrepancy. Why would it be greater than if I remove it from its support?
That's why. Would it be like if you're holding